Hello, I'm Dr. Patricia Shaw, and welcome to the third video in this series of robotics programming with Robot Benchmark. In this video, we'll be looking at the challenge on Robot Benchmark for the square path. So before we get started, let's have a quick look at the challenges we've done so far. The first challenge involved traveling a set distance in a straight line. It was a very deterministic approach to solving the problem, and it used the position control mode for the robot. Whilst the next challenge, challenge 3, involved obstacle avoidance to be able to cross a room, and it was purely reactive controller that was used there, sensing the environment with the infrared sensors, and hopefully you use the compass as well to navigate in as straight a line as possible across the room. And of course, that was using velocity control. So let's have a look at challenge 4, the square path. So here we have the robot that's been used in this challenge, and the aim is to drive around this square carpet, it's 2x2 carpet that's shown in the simulator, as accurately as possible. So this is a very deterministic plan that we need to be able to follow. And there's not a huge amount of sensor data that we can actually use to guide the robot. We don't have any obstacles to guide the robot or walls that we're following here. So we refer to this as quite an open loop control system, whereby essentially we're telling the robot what to do, but we don't have a huge amount of feedback from the environment telling us how we're doing. In terms of measuring the success of this particular challenge, then it does give you a breakdown per side and then an overall score. And for the default starting program, you can see what that actually looks like on the right here. So for each side of the square, it gives you the average as to how well the robot has followed that particular line. And it also draws out the path that the robot follows in relation to the four sides of the square. So what are the challenges here? Well, to some extent, this is really starting to emphasize some of the challenges of operating robots in the physical world. Now, obviously here we are still using a simulator, but the simulators are trying to bridge the gap between virtual and physical worlds as much as possible. So that means that they do actually try to incorporate some of the physical issues that we encounter when working with robots in the real world. And this can include things like wheel slippage, so the wheels rotating without actually moving the robot. So think of this as the wheels of a car spinning on the spot without actually driving forward or where they lose traction. Inevitably, when we're working with robots as well, there can be slight variation between the motors. So the left and right motors might drive at slightly different speeds, and so you end up with the robot steering off to one side. And that can be emphasized over time with wear and tear on the motors. Surfaces are very rarely perfectly smooth or perfectly even, so subtle variations in a surface as we drive along it can actually throw the robot off course. And of course, the type of surface that you're driving on here can make a difference as well as to the amount of friction that the robot is encountering. Now, I can't say for certain in the simulator. If I go back a moment, you'll see that it's the sort of wooden parquet floors that they've got around the outside, and then the carpet that they're using in the middle. I can't say for certain if they are actually simulating the different physics of those two surfaces and the different impact that would have. But in reality, that would actually make a big difference to the robot. So one wheel would actually be moving more slowly than the other because of the higher friction on that wheel. You might get more wheel slippage on the wheel that's on the smoother surface. So those are some of the challenges that we would have. But actually the real challenge that is very much simulated and definitely impacts us in the real world as well is that when we set a speed or velocity for the robot to travel at, it isn't instantly traveling at that speed. It does take time to actually reach that speed and then also to slow back down again from that speed. So If we tell the robot to travel at a set speed for a set distance, our simple maths might say it's travelled speed times distance. Speed equals difference over time. But in reality, it won't actually have travelled that far because there will have been some time taken to reach that speed. And then if we're actually gradually slowing down when we get to the far end, then we need to take that into account as well. So we have to deal with the real physics of the world when we're actually operating robots, even in simulators. So how do we actually go about estimating how far we've travelled? Well, this is something called dead reckoning, whereby we try and calculate the position of the robot from wherever it started from. And that can be against global coordinates. So if we had access to something like GPS, then dead reckoning would make use of that GPS to tell us exactly where we are with a certain level of accuracy within the world. But usually when we're dealing with robots, particularly indoor robots where we don't have access to things like GPS, then this tends to be the distance travelled from the starting point. And this is very much an estimate-based system because with all of the physics I previously mentioned, it's actually quite difficult to say exactly where we are, but we do tend to try and make an estimate based on various different properties. So one of them is the speed at which we've been travelling and the direction which we've been heading. So what speed has been sent to each individual wheel in order to be able to set a heading. And of course, how long we've been travelling in that direction for. But those will give you very rough estimates. And over time, the further you travel, the greater the error from that. Now, later on, we could potentially start to build up a map of the environment using the sensors to be able to start to recognize features in the environment. And as you build up that map, you might start to be able to localize yourself a bit better within it. But I won't go any further on that today. But what we can use is a particular type of sensor that isn't always included in robots, so particularly not the cheaper end, but as we get more sophisticated robots, then we tend to get something called wheel encoders. And these are a type of sensor that's able to track the movement of a wheel. And what it tends to be is what we've got here on the right. We have a disc that's got a series of holes around it, around the outside of the wheel. And there's a light that's then shining through, and there's a receiver that's detecting that light. And as the wheel turns, this disc also turns with it. And you end up with the light signal being detected as blocked and visible. And that gives us a very nice digital signal that we can measure. Now, in this particular case, we can't actually tell which direction the wheel is turning, only that it is turning and what speed it's turning at. So there are some more complex versions of this where they are actually able to tell which direction the wheel is turning in. But the general principle is that you have a light shining through, and as the wheel rotates, you're able to measure how fast the wheel is actually turning in. And so that can give us an idea of how far we've actually travelled. And that will take into account the acceleration up to the target speed. And because we're measuring both wheels, we can also measure the direction a little bit more. Wheel slippage is still a bit of a problem because the wheel will move without the robot actually moving. And that's something that this doesn't enable us to detect because we will still see that the wheel has moved. But it does give us a slightly more accurate idea of how far we've travelled. So let's look at the robot that they're using in this particular challenge. And it's the Pioneer 3-wheel robot. So this actually has two large drive wheels, one on either side at the center point, and then there's a caster wheel at the back that's free moving. Interestingly, there is a 4-wheel version of this robot. So the 2-wheel version is differential drive, and the 4-wheel version, whilst differential drive, the wheels aren't steering, so it is actually a skid steer system as well. But here we're just using the 3-wheel. Now the front and rear, so these gold discs that we can see around the front of the robot here are actually sonar sensors, and there's another set that go around the back of the robot. We're not actually going to be using those in this particular exercise, but they might well come in handy for a later exercise. And it does give us in the challenge description the dimensions of the wheels and separation of the wheels. So if we do actually want to try and calculate some properties about how far this robot's moved, then we can use that information. One other piece of information that it doesn't actually give you in the instructions, but is accessible in the program, is the maximum velocity at which the robot can travel, and that's described as 5.24 meters per second. This particular challenge, though, isn't about doing it as fast as you can, it's about being accurate. And so you might actually find that using a slower velocity enables you to gain a greater accuracy than simply going through it as fast as you possibly can. But if you are interested in the maximum velocity, then there it is. With the Webot simulator, if you try and go faster than the maximum, it will give you a warning an error in the simulator. So let's have a look at the challenge a bit more precisely. So actually, before we do have a look at this, I'm just going to jump over to the simulator and have a look at the starting program that it gives us. So here we've got the simulation, and I've just loaded up the control program that it gives us as a starting point. So once again, we're importing the robot and gaining access to the controller for the robot. And of course, we're gaining access to the left and right motors to be able to control the wheels. We then have a for loop, a Python for loop that will repeat 4 times. So it's repeating it once for each side of the square. And interestingly, although in the instructions here it suggests using a velocity controller, what it actually has here is a position-based controller. So similar to what we were using in the first challenge, officially the second challenge, is a position controller based on how much the wheel is actually rotating, or how far the wheel is rotating in order to reach a set point. And so we're setting positions there, and this robot dot step is then actually a wait function to allow the robot to travel that distance before executing the next action. So this is like a sleep function. Interestingly here, there is some, I'm not going to say competition between these, but the two can be adjusted in parallel to achieve different effects. When we're going in a straight line, we're setting the same distance on each wheel in a positive direction. But when we get to the corners, we want one wheel to turn forwards and the other wheel to turn backwards. And that means that the robot will turn on the spot. And specifically, if we're turning the left wheel forwards and the right wheel backwards, then the robot will turn to the right. We then have another sleep pause there, and that should then complete the first side and be back to starting on the second side. If we want to switch over to velocity control, then we would need to set the position to infinite, and we can set velocity to a target velocity we want to use. Here is just then setting velocity to 0 to fully terminate the simulation. And as I say, if we run this particular program as a starting point, just load up the metrics, we can track the robot as it's moving. It seems to do quite well on the first side, but on the second side, you can see it's drifting off, and then cumulative error is drifting off further and further with each side. There we go. So let's go back to the slides a moment. So the challenge, as I say, it starts off with a position control, but you could of course switch it to a velocity control. But you need to remember that the velocity is in radians per second, not degrees per second. And what we want to be able to adjust is how, either in position control, how far the wheels turn. In velocity control, it's how long is it traveling at that speed for. And target is to travel in a 2 meter square. Simply adjusting the timers will gradually improve the performance, but it is actually quite imprecise. And if we want to try and make a more intelligent estimation of the values that we need for those timers, we could actually do some calculations based on the kinematics of the robot. So using the length, which is the separation between the wheels, the radius of the wheels, and then using that to calculate the velocities of each individual wheel with the distance that we want to travel and the specified speed in order to calculate the duration, the time that we want to be traveling for. So we could use the kinematics to calculate it, but actually what they really want you to do is try and use these wheel encoders, or wheel sensors, wheel position sensors as they call them in the simulation, to be able to work out when we're reaching the corners and therefore when to stop. As with any sensors, there is some sensor noise, and they do simulate sensor noise in the simulator, and you'd most definitely get a lot of sensor noise on physical robots. So there is some sensor noise here, so it's still not going to be 100% accurate, but potentially using the sensors could actually give us a bit more control in terms of achieving this task. So how do we go about adding those sensors? Well, first of all, if we want to change from position control to velocity control, as we had in the previous challenge, then we set the position to the float infinite for both wheels, and then we can set the velocities for controlling each of the wheels. As I say, if you want to find out what the maximum velocity is, you can actually obtain the maximum velocity using this get max velocity attribute of one of the wheels, and then you can print that out. So it's quite a useful function there that you can gain access to. And then you can set the velocity that you want to use. Now, this doesn't have to be a constant, especially if you're using the sensors, but initially you can set a velocity in there and then calculate times or just timings based on that. So if we do then want to develop the solution a bit further and start to add the sensor readings in, then here's how we actually add the sensors. So much like we were adding the infrared sensors for the previous robot, here we can gain access to the position sensors for a particular wheel, and we then need to enable it with and the 16 in the round brackets there tells us how often that sensor will actually refresh. And we can do that for both of the wheels in order to be able to track how far they've moved. We can then obtain the current readings from those sensors, and we can print those out to be able to track how far we've gone. So what are the tips for tackling this challenge? Well, first of all, you may want to have a play around with it in position mode. Try adjusting the distances and the timings just to see how close you can get it. I would then encourage you to try switching it over to velocity control, and you might want to do this by defining functions, one for position and one for velocity control, so you can compare the performances. So then adjusting the velocity that it's traveling at and the times that it's traveling at that velocity in order to complete the square, and see which is perhaps easier or harder to control. But if you are using the wheel encoders, then you will want to be in in velocity control. My mistake. You want to be in the velocity control whilst using the wheel encoders. And whilst you've got those wheel encoders and one of either your position or velocity controllers running, you can perhaps print out the values to try and find out roughly where it wants to be as it gets to those corners. You can then adjust your program so that as it gets closer and closer to that corner, It actually slows down the robot, and the slower you're going, the more control you've got over it, the greater the accuracy you'll have. So as you get closer to those target encoder values for each of the corners, you can start to slow down the robot in order to be able to accurately stop at the right point, make the turning for the right amount, and then continue. Now remember that you may want to use relative encoder values, so you're not taking absolute reading, but you're comparing that to a previous reading, so the start reading, and how far it then needs to go. So you're not having to separate out the for loop and to do each side separately, because those encoder readings will keep building up. But hopefully that will give you a good attempt at the challenge, and all the best, and we'll see you next time.